Good morning, everybody. Today is a terrific day, and I'll tell you why. So, as you may have known, I just moved, and I've got a lot of things set up, including a brand new, well, it's not brand new, it's 3 years old, but my 3-year-old desktop computer, which I haven't had for a long time. And that makes it amazing because I now no longer have to wait for my computer to be loading things. Now, I say this as I'm waiting for Codeforces to load. On top of that, we've got a Codeforces round today, which just started. So let's begin that and have some fun. All right, problem A, fence. Yura is tasked to build a closed fence in the shape of an arbitrary, non-degenerate, simple quadrilateral. Okay. He's got 3 segments. Now he wants to find some possible integer d, 4 segment, so you can build them using the 4 segments. So it's just the sum minus 1. Yeah, okay. Let's do that. That is always some valid answer. Yeah, I buy it. Oh man. So I probably could have gotten a 0-minute solve today. That may have been the first time ever where if I had it set up right, I would have gotten it, but that's fine. All right, there you go. Problem A. Wrong answer, test 2. Brilliant. Let's read the problem again. Does not cross itself. Longs, okay. Brilliant. Well, that's fine. Read the problem carefully. Okay, let's get CF notifications up. All right, we got it. On to problem B. A matrix of size n by m is called nice if all rows and columns of the matrix are palindromes. Sequence of integers is a palindrome. I know what a palindrome is. She owns a matrix of size n by m. In one operation, wait, Sasha's a boy? Okay. Sasha can increase or decrease any number in the matrix by 1. He wants to make the matrix nice. Interesting. So you have 4 numbers that need to be the same. I'll draw a picture here since it's a Div2 round and not rated for me. And we've got whiteboard, and whiteboard is now fast and speedy, and I don't have to wait ages for it to to leg out on me. So if we've got a matrix that looks like this, then this space here and this space here needs to match because this is a palindrome. And then also it needs to match this last space because this is a palindrome, and then this space because these are palindromes. So these 4 need to match, which means we want to pick the second of those operations. Or the second biggest of the 4. So that's not too bad. So it's height equals this, width equals this. All right, so now we have the board. Now I'll keep track of whether each thing was used in order to avoid double counting. Yeah, so it's tricky because like the middle cases might be annoying. So anyway. Then we'll also need to store total cost. All right, so now the other x will be width minus 1 minus x, into y will be height minus 1 minus y. If this is already used, we can skip it. Then we've already accounted for the space. Otherwise, used at xy equals used at oxy equals used at xoy equals used at oxoy equals true. And now parts dot add a at xy. Oh, we can do this better actually. Yeah, let's say this. So if not used at xy, do this. And now used at xy equals true. And then we can do this even better. So now int array x's equals x, x, ox, ox. Y's will be y, oy, y, oy. Clean code club. Look at this. So now int nx equals x is a d and y equals y is a d. So clean. Okay. So we add all of these things to our list. Now we'll probably want to sort this. And then we'll pick the split index. That'll just be the median of this. So this will be parts get parts dot size divided by 2. Is that right? 2 divided by 2 is 1. 3 divided by 2 is also 1. So that's fine. All right. So then for int I in parts, then cost plus equals math.abs of I minus split. 842 looks good.
Well done, sir. AC on problem B.
Awesome. All right, problem C, bargain. Sometimes it is not easy to come to an arrangement in a bargain. Right now, Sasha and Vova can't come to an agreement. Sasha names a price as high as possible, and Vova wants to remove as many digits from the price as possible. In more details, Sasha names some integer price n. Vova removes a non-empty string of consecutive digits from the price. The remaining digits close the gap, and the resulting integer is the price. I see. So if you remove 1, 3, 1, 2, then you're left with 1, 2, 1. It's allowed for the result to contain leading zeros. If Vova removes all digits, the price is just 0. Sasha wants to come up with some constraints so that Vova can't just remove all the digits, but he needs some argument supporting the constraints. To start with, he wants to, this probably should be bigger, huh? To start with, he wants to compute the sum of all possible remaining prices after Vova's move. All right, that is not obvious. Let's head to the drawing board. Control, is that not how you move? Huh. Well, I guess we'll just erase. Okay, so we've got some number. Doesn't really matter what these digits are. Then we care about sum of everything, right? So what if we did a DP? I guess so we care about the index. The index is definitely important. What else matters? Well, there are three things, right? So we can either, if you've got some range you're gonna delete, you can either be in like part 0, part 1, or part 2. If you're in part 2, you know everything after you will matter. If you're in part 0, it's tricky. Because you don't know how much this digit matters for you. So that's not really going to work. All right. Let's not do that anymore. Let's instead think about the fact that we're considering all ranges. So this thing gets used. We can do some n choose k stuff probably to consider how many times this gets picked and how big it gets picked each time. So we know what the digit is. We know how many times it can be, the range that gets deleted can be in this half. That's pretty easy. The tricky part is for this right half, because we're not sure, like we can figure out how many times this will get picked, but it matters how many times each length gets picked. It can be pretty big. Okay, it is actually hard, so I'm not missing something obvious. So let's say this value is value x. It's x times 10 to the 0 times the number of ways there are of choosing 10 to the 0. So that is 4 choose 4. It's not 4 choose 4. We've got a range of size 4. But you just pick one position. So that's times 1 plus 10 to the 1 plus x times 10 to the 1. So that means we have one space left. There are 2 ways of doing this, times 2 plus x times 10 squared. So in this case we leave 2 open. There are 3 ways of doing this, times 3. Okay. What happens when we move over by 1? Yeah, okay, so this is not going to be too bad. I think we can do this pretty easily. We only need, we need n choose 2 And choose 2 we can do without dividing anywhere, so that's easy. We don't need to do factorial inverses. Then this part, I think, is pretty easy to maintain. So if we go from one position to the next, we've got this. If we move it over by 1, we'll keep the x part separate. So we'll do x, and this is like 10 to the 0 times 1, plus 10 to the 1 times 2, plus 10 to the 2 times 3. Then we'll need to add a 4th term. So we'll need to add 10 to the 3rd times 4. So that's the idea. Yeah, we can handle that. All right, so single test case, huh? I think they predicted that it would be difficult correctly. Char array line will be this, to char array. Int array values is new int array line.length. All right, so we have all of these things. Now we need to consider this total. Okay, so we're going to need our math methods. So long add, long a, long b, a plus b, mod mod plus mod, mod mod. We'll also need a multiply method. Also need our mod. All right, so yeah, okay, we've got all that. So now we'll want to consider each possible value. So int position. Do we want to invert this? Let's do that, actually, that sounds beneficial. So we'll have the smallest part of the line come first. Okay. So now for int I in values, we're going to need some stuff. Okay, so long total will be 0. We'll print that at the end. Then we need to consider how much each thing matters. So we're also going to need this long, like this, this 10 thing. Which I'll just call this initially. We're also going to need, so what happens here? We take this. Yeah, we're also going to need the next 10 pow. Okay. So long 10 pow will be 1. And then long multiple will be 1. Okay, so now after we do each step, we need to say 10 values equals add 10 values, and then multiply the 10 pow by the multiple. Then we need to increment the multiple. And then increment the 10 power by a multiple of 10. All right, so this maintains all of these values. So this will keep track of this bottom half here. All of these 10 to the 0 plus 1, etc. So now we need to count how many times does this thing get chosen. So it's possible range is on bigger numbers. Int n bigger numbers will be n minus 1, and then n bigger numbers minus minus. We probably also want n choose 2, just to make it easier to think about. So n choose 2 will be, I'll return n times n minus 1 or n plus 1. This just makes sure it's positive under mod. So does this work? 1 choose 2. In reality, it's 0, but 1 times 2 over 2, yeah, so this is what I want. It's like the number of ways of deleting some range of this size. So in this case, total equals add total. So we can pick any two numbers that are bigger than us, and choose 2 of bigger numbers. And that's, for each of those ways, we will be counted. Oh, we need the power of 2 as well. So we need this times 10 pow. Yeah, okay. Then we also need the smaller numbers. So now total equals add total to, oh man, this is getting messy. Okay. Oh, and I'm missing another, I also need this I multiplied by itself. So I times the number of ways we can pick bigger things times this 10 pow, because we know how many digits we have. Okay. Then this is delete smaller numbers. In this case, what are we doing? I times the 10 values. That's what I called it. Oh my goodness. Oh my goodness. Man, math and magic, I tell you. All right, looks good to me. Let's move on to problem D then. Returning home.
Well done, sir.
Here we go, we got it.
AC on problem C.
Yura has been walking home for some time already and is planning to return home. He needs to get home as fast as possible. To do this, Yura can use the instant movement locations around the city. Let's represent a city as an area of n by n blocks. Yura needs to move from one block with coordinate start x, start y, to the block with coordinates fx, fy. So start to finish. In 1 minute, he can move to any neighboring side blocks, in other words, up, down, left, right. Also, there are m instant movement locations in the city. The coordinates are known. He can use instant location. Wait, what? He can move to an instant movement location if he is located in some block with the same x coordinate or the same y coordinate. Smallest time to get home. So n is quite big. Oh, it's n by n. And then there are m teleportation pads. I see. This is actually kind of interesting, I think. I kind of like the problem, to be honest. I don't know how to solve it, but it sounds kind of cool. So you've got some grid, huh? You've got like a big grid. They say you start in the bottom left. You start somewhere and you move somewhere else. Okay, that's kind of annoying. Well, let's say you start in the bottom left, maybe just for simplicity. So you have like this position here, which you can get to in either this time or this time. You might also have something here, which you can get to in this time here or in this time here. Do you have to pay to, in no time? I see, got it. The 4 directions are yeah, okay. So basically all of these nodes here they can all go to this here for free. Same thing with all of these nodes. Okay, so if you're at some position, how would we go about doing this? Well, whatever the smallest y value is, we could go there, or we could go to the smallest x value. So we could kind of do like a Dijkstra sort of thing in that sense. Whichever one is closest, we could go to it. And then, what would we consider? Oh, can we just add edges to the graph like that? Go to either the first thing to your left, right, up, or down. Yeah, I think that works. So, because, yeah, here's why. So here's the proof. If you've got some point like this, some point way out of here, like way in the middle of nowhere, and then some point like this, if you were initially going to just travel like this, that's fine. But instead, what you could do is travel like this, teleport here, and then travel like this, and then you'd be here with the same number of steps. So that's an exchange argument. So we can add edges from each node to the first node in all directions of it. Can multiple nodes share an x or a y? Because that's kind of wacky. Not in samples. That's like an important constraint though. Well, I think we can handle that anyway, just with Dijkstra's. But it's hard to handle. Yeah, that's annoying. Because, like, of how things work. Yeah, we can handle it if we tie-break our sorts. Okay. So yeah, so we do the Dijkstra's and then we brute force the midpoint. Yeah, okay. All right, that's fine. So what does input look like? N by n, which we don't really care about. And then what is this? 3. Oh, 3 points. Yeah, okay. So we'll skip this n. And then we care about the number of points. Maybe we won't do the comparator here. Okay, so we also need to know the start point. And the end point. Okay, so we've got this, blah, 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 blah. Now we need our edges, array list vec adjacency equals new array list, and then array list vec cost equals new array list. Then we'll probably want a long D1 and then D2, both of which can start at, well, long.max value. Okay, then we'll want our Dijkstra's, static void Dijkstra's from vec from. We need a state. And a long distance. All right, so now priority queue, state queue, and priority queue. While this PQ isn't empty, we'll get the next state. If next.distance is not equal to next.n.d1, then continue, because we don't actually use this state at all. Otherwise, for into I equals 0, I is less than next, well, yeah. Whoa. Kind of messy, but that works. Node 2 will be next.n.adjacency.getI. These are vectors here. And then we also want the cost. Now, who thinks this is a good idea? Why would we suggest toString rather than n when I type in n? That's kind of silly. But anyway, cost.getI. Why did they did it again? Oh, this should be oblong. Yeah, okay. All right, so if new cost is less than 2.cost, then 2.cost equals new cost. And, or 2.d1. And then we need to add a new state to node 2. The distance will be 2.d1. Okay, we keep doing this until we're done. Finally, we just need to say from .d1 equals 0. We'll probably want to pass in all of these. And then pq.add new state from, are they telling me I've misspelled it or something? I don't know, it's kind of weird. Add a new state to from, distance will be 0. Okay, so we've got our Dijkstra's. Now we just need to build this graph. Yeah, okay, so well, let's actually use the Dijkstra's first. We'll build the graph in a minute. How do we do this? So this will calculate the distance from the start to everything, from the end to everything. And now we can say for vec v in points, well, long ants will be start.x minus n.x plus math.abs start.y minus n.y. And for each intermediate point, ants equals math.min of v.d1 plus v.d2, or just whatever the answer was. Yeah, okay, that should be fine. Then finally we print the answer at the end. So now the one part we have left, I think, is just to build this graph. How do we do this? We need to sort this. Yeah, okay. So now we can add edges between each of these points. Points at I-1 dot adjacency dot add points at I. Okay, so this builds that for all of the points. We need to do the same thing for y's. Sort by y here. We'll rename this dy just so it makes sense to us. And then finally, we need to add edges from the start to everything and from the end to everything. So for vec v in points, start.add, adjacency.add v, start.cost.add math.min of math.abs, start.x minus v.x, or math.abs start.y minus v.y. This needs to be a long, doesn't it? All right. Well, that's fine. And then we do the same thing for the end. So these will all be one-way edges, but that shouldn't be an issue. We'll do our Dijkstra's and we're done. Okay. Zero. Ah! Okay, that's fine. So we start at this, we end here. Let's see what's wrong here. And it should be not too bad. Okay, so 4-1 should be 0. That's fine. This should also be 0. Am I not doing the second DFS from the right position? Oh, wait. This shouldn't be start. This should be end, and this should also be end. Okay, cost is 1. Should it really be 1? Should be 5. What? Yeah, okay. Euro needs to reach 5-5 from 1-1. You can do that in 5 minutes by using the second instant motion location. So now he's at 4-1. Oh. Huh. Okay, this is not right. This shouldn't be the min, this should be the sum. The reason for that is the edges are like different in the two directions. In one way, you can teleport, and the other way you can't. So that's why that's wrong. Makes sense though. 42. Man, this is taking me a while. I don't know why, but all right, we got it.
Well done, sir. AC on problem D.
How are we doing? 32nd place. Not bad, not bad. Okay, on to problem E then. Here we go. Min Lexes. Some time ago, Lesha found an entertaining string S consisting of lowercase English letters. Lesha immediately developed a unique algorithm for this string and shared it with you. The algorithm is as follows. Lesha chooses an arbitrary number of pairs on positions I to I plus 1. Okay, so she picks a bunch of adjacent pairs. And for each pair, the inequality holds. Okay, that's not helpful, I don't think. For each pair, the equality, oh, they're equal. There is no index contained in more than one pair. So you take this, okay. She removes all characters on these pairs and the algorithm is over. Interested in the lexicographically smallest strings. It's a boy again? Lesha? Really? What a name. Okay, anyway. Interested in the lexicographically smallest strings you can obtain by applying the algorithm to the suffixes of the given string. Maybe, okay, maybe it's not actually a boy. Maybe there's doing what, like, makes a lot of sense, which is using he as just like a gender neutral pronoun. Because if you're going to pick one, I think that's the way to go. Just use he. Same thing Latin did, same thing English used to do. Makes a lot of sense. That way you maintain the plurality of the sentence. Okay, so Lesha has some strings you can obtain, or the smallest, what do you want? The lexicographically smallest string you can obtain by applying the algorithm a bunch of times. So you can delete any even continuous, like if you have a continuous block of characters, you can delete any like range of them. Wait, what? What is this? Oh, to suffixes of the given string. Interesting. So it seems like this is basically suffix arrays, but with some modification. So suffix arrays is if you have some string, you want to sort all of these suffixes. Oh wait, no, that's not true. So it's only true in this case because it happens to be sorted, but it can be better. Yeah, this would be lexicographically first, this 0. So it's not suffix arrays because you don't sort it. Okay. So we just want to know, like, what does this look like, basically? Do we print the length first? Yeah, first we print the length of the string, then the string itself, but like in a compressed form. Well, I imagine it's easier to just go backwards. Okay, if we go from bottom to top. Oh, okay, now control click is working. So yeah, so if we go, let's say we end with well, let's do this. Let's do the cab. I think that's a good example. If we have the cab, if If we have just a B, the answer is just a B. What if we have an AB? Well, we know the next character is a B, so we'll leave the A. What if we have two A's and a B? Well, we know the next character is a B, so we'll leave it. What if we have a C? Well, then we'll keep this C, or we keep the C because we have to. But if we have another C, we care about, okay, this would be an A, so we would want to delete these C's. Yeah, okay. And then nothing ever changes because you delete everything all at once, so you don't have like things compress. So this seems like not a very difficult problem, to be honest. All right. We just have to be kind of careful in the implementation. So there you go. There's the line. And now we want all of our answers. Okay. Yeah. So printing is going to be messy, but we'll do it at the end. So then we'll need a print writer. We have to go backwards. For the I equals answer dot size minus 1 greater than or equal to 0 minus minus. Then out dot print line answer dot get I, then close. All right, so now we just need to actually generate all of these. So what do we want to maintain? The length. That's true, length for sure. We also want the next unique character. Initially, we'll have it be a minus 1. Does that sound fair? Yeah, probably. Whatever comes before a, they're all lowercase, right? Yeah. So that means like we want it to be empty if possible. Okay. So now, what is a minus 1? I'm just curious. Backtick. Huh. Cool. What is z plus 1 then? Curly brace. Interesting. Okay. Well, the backtick. Interesting. I didn't know that. Anyway, so now let's go through each character in the line. So how do we do this? So for int I equals length is 0 initially. I equals line dot length minus 1 greater than or equal to 0 minus minus. Char last char will be next unique. Okay. So do we also need the count of these last characters? I guess a stack is probably the way to go. Yeah. A stack is just the easiest. That's basically what I'm dealing with here. Okay, fine. Well, let's just make our own custom stack. That way we can read from it. Okay, so now int head will be 0. Well, I guess the front will be 0. The front will be -1, and it'll be 0. All right, so now what do we want to do here? So if the stack, well, if end front minus end plus 1 is 0, then the stack is empty. Then stack at front, well, at plus plus front will be equal to C. Yeah, I think we don't really have a choice. Okay, what else? So otherwise it's not empty. So now, if it isn't empty, we care about whether we're the same as the previous thing or not. Oh wait, I haven't handled the case yet. So if we've got like some C's, okay, that's fine. Now we see a B. If we see a B, we want to delete as many C's as possible. Yeah, so what matters is this thing. This is important. As long as this is less than C. If it's bigger than C, then we'll never use it. We see another character. Yeah, okay, so this is important. So then if it's less than C, it matters. Yeah, okay. Int next important equals -1. The same as previous, then what do we do? We might want to delete both. So yeah, when would that be? We want to delete both of them if we're bigger than next important. So if next important is equal to -1, or stk at next important is greater than or is less than C. Then front minus minus Otherwise, we want to add ourselves to the queue, but we aren't relevant. So yeah, okay. So then STK at plus plus front equals C. So this means we're indifferent. So if we care about whether we are, oh man, this is confusing. If the next important is the front of the queue, then whatever the previous thing was just deleted entirely, so we can ignore it. Oh, well, I guess it doesn't matter. We can just say next important will always be the front of the queue. Yeah, because we can't change it anyway. And then, if we're different from the previous one, we don't have a choice. So STK at front plus front equals C. This end is never used. Okay. All right, so finally, int length will be front plus 1. If length is less than 10, or less than or equal to 10, or less than 10. 1, 2, 3, 4, 5. Yeah, okay. So if it's less than or equal to 10, then do one thing, otherwise do this other thing. So in this case, string builder res equals new string builder, start with just this, plus a space, and we want this string what is I? Oh, it's that. Okay, fine. We'll make I this. Okay, otherwise, we want the same thing for int j equals front, j is greater than or equal, greater than front minus 5, j plus plus, minus minus, res dot append, stk at j, res dot append dot dot dot, and then res dot append stk at 1, and then stk at 0. Okay, then we print all of them. Think it works? That would be very impressive now, wouldn't it? What do you mean? Ah, yes. Answer.add res. It doesn't crash though, that's nice. So much for clean code. 3, 2. We can't continue. ABC, BC, 0, 1D. Okay. Let's just do this here, and this here. Are these the same? This is when it would be really nice to have a terminal to check it for me. Let's just run through the numbers, I guess. 9898, 765, 654, 3210. Yeah, I think that's fine. Let's submit. And I'll look through it if it's not fine. Okay, hopefully it's fine. That leaves one problem left. How many pretests were there? 14. Okay, not the end of the world. How are we doing? '21st place. Not the end of the world. Not the end of the world. Pretty good, actually. We just have to get problem F now, which apparently is very difficult to get right. Yura owns an ordinary and boring, a quite ordinary and boring array A of length n. You think there is nothing more boring than that, but Vladik doesn't agree. I would never think that. If you own an array of length n, that's a very special thing to own. Anyway, after all, why else would people give you arrays of length n for your birthday if it weren't so special? In order to make Yara's array even more boring, Vladik asks Q boring queries. Each query, this is a great round. I'm loving it. Each query consists of two integers x and y. Before answering a query, the bounds L and R of this query are calculated. L equals... Oh, they're forcing it online? Yeah, okay. So it's just forced online. So two L and R bounds for the array. Wait, can R be to the right? Okay, yeah, you swap them. Okay. After Vladik computes L and R for a query, he needs to compute the LCM on the segment. Okay. Yes. What? Compute the LCM on the segment of the initial array, mod 10 to the 9th plus 7. So you're telling me this is just range LCM. For real? That seems not correct. Range LCM, really? So it looks like they were just trying to stop Moe's. Or just, I don't even know. Huh. I thought this would be an easy thing to do. Is this really that difficult? Okay, well... I don't know. Maybe this is a boring question, but I think it's pretty good. To be honest, I've liked this set. I thought this was a good set. Maybe it's just because I'm in a good mood today. But I thought the problems were all interesting. And I think this is an interesting problem too. Yeah, I got kind of... It's the first time I've gotten problem A wrong in a while, but that's fine. How do you do it? So bounds are like generous, that it seems like maybe they're looking for like some n root n stuff. If we want the LCM of two numbers, we know that the LCM of A and B is equal to A times B over the GCD of A and B. Is that helpful? Well, GCD is kind of tricky. Like if we're going to do this with a segment tree, A times B is easy. This is easy. Like that's, anybody and their mother can do this. How do we do the GCD of two numbers? That sounds kind of difficult. We've got a product of a whole bunch of things here, a product of a bunch of things here. We might have a bunch of this might be like 2 to the 5th times 3 to the 5th times 5 squared times 7. This might be 2 squared times 3 cubed times 5 to the 4th times 7 to the 5th or something. So we need to take the minimum of all these exponents and then like multiply the things together. Alternatively, we need to find the max of all of these exponents, which is just the problem we're trying to solve. Let me make sure I'm not misunderstanding the problem. Is there any... What's up with Discord? Am I going to regret doing this? Yeah, probably. Oh, wait. Uh-oh. Oops. Huh. Well. Yeah, it's kind of... Huh. Should have thought through that better. Let's see. Because this definitely takes priority over this Codeforces around that isn't rated for me. Oh, no. Darn. I guess I'll keep doing this then. Oops, my bad. Anyway. So we want range LCM using the fact that all numbers are small. Yeah, so the LCM can be very big. What would be helpful here? Is there like an intermediate problem we could use? So what if we split it into square root n blocks? So now for each query, we have the exponents for everything. And then we have to cover root n of these blocks. Then we max the exponents. Oh, but this doesn't actually work because it's still, now it's n root n per query. Yeah, storing something that's size n in each of these square root n blocks is not super helpful. Although, well, only square root n times log things matter. But like, if we're going to be modifying all of those, we might as well just do the query naively. Yeah, this doesn't work though. Because you're under mod. And the numbers get huge. Is there a better way of doing this? Oh, we can do it. Well, how many primes are there? Maybe that's helpful. Because if there aren't many primes, we can use an RMQ for each prime, possibly. There are, what's going on? If prime I times I less than or equal to n, there are 2 times 10 to the 4 primes. There are 2 times 10 to the 4 primes. How many of those primes are big? Yeah. So if it's less than or equal to max n, then real count plus else big count plus. So there are a bunch of these things that can only occur at most once. It's about half of them. That's way more than I would have expected, to be honest. $7,000? Really? Half of them are less than the square root? Okay. Well, 7,000 RMQs, I don't know that cuts it. What about I times I times I? Wait, what? If it's less, that made it bigger? Oh, yeah, this was it. There you go. There are 86 small primes. 17,000 big ones. Yeah, that makes a lot of sense. Okay, so for these 86 small primes, we can do an RMQ. For all of these big primes, we need something better. Yeah, okay. So 86 RMQs will be helpful. But now we have roughly 2e4 that can occur 0 or 1 times. So how do we handle all of these? Slightly simpler problem, maybe. Yeah. Well, only one of them can occur at each position even. So that might be even more helpful. We can't even iterate through each of these things for each query, though. Like for each of these things, we want to know, is there a 1 in this range? If there is, multiply in this number. So we want something where like it's off up until a certain point, then turns on, stays on. Yeah, it's tricky because we don't want to, if it occurs twice, we don't want to multiply it in twice because it'll only be in the LCM once. Can we make it better? Yeah, I don't know. It's forced on line 2, right? So it's forced on line. So the problem is really simple, just like LCM of a range on line. So yeah, like this doesn't sound like it's possible to do in general. So I think we have to abuse the fact that the numbers are small. Is it like a 4 Russian sort of thing? Is that what they're looking for? Divide out a log? Seems like it would be pretty much the right runtime. Most of these are wrong answers rather than anything else. Hacked? E is hackable. Hang on, let me make sure I'm not failing system tests here. Why would E be hackable? There are a lot of reasons E could be hackable. It's very touchy. I'm not gonna worry about it. If I get hacked, I get hacked. I think I'm also gonna pause with F and work out what's going on with running this set with my team. Because I think I should focus more on that. That's way more important than this. This is just kind of extra practice anyway. So yeah, I'll read the editorial for F. I don't know what to do. I don't have a good solution path. And it seems like most people don't either. So this would be, it's interesting. It's an interesting problem. Honestly, I thought the whole set was interesting, to be honest. Yeah, I enjoyed it. Let's talk about solutions, I guess. It's a bit early for sure. And obviously I won't publish the video until contest is over, because I don't want to cheat. That would be bad. But I don't think, yeah, I have to talk to my team, so I don't have time to do F, I guess. But that's fine. All right, let's talk about the problems. For problem A, you want to make a quadrilateral, but you want to make it so that like the fourth side that you choose can be whatever value you want, and you want to pick some fourth side that makes it a valid quadrilateral. So first, I guess let's talk about what does it mean for something to not be a valid quadrilateral, or to have four sides that can't be a valid quadrilateral. So if you have one side like this, one side like this, one side like this, and one side like this, like they're not going to reach, so it's not going to be a quadrilateral. Namely, if you've got like A, B, C, and D, if D is greater than or equal to A plus B plus C, this is a D here, doesn't look like it, then that's impossible. So we want to avoid this for any association of A, B, C, and D. Now it's possible A might be really long. If A is really long, then we can't have D be too small, because if it is, then D, B, and C won't be able to reach A. So we want D to be long enough where that's not an issue, but we also don't want it to be too long that it creates an issue. And in particular, you've got all of those constraints. We're going to make it always like as long as possible so that it'll always work, but just barely short enough that it doesn't create the issue. In order to do that, what things would look like is we need to be, D needs to be less than A plus B plus C. So we'll make it a plus b plus c minus 1. Of course, each of these can be up to 10 to the 9. So you have to use longs because 3 times 10 to the 9 doesn't fit in an integer unless you can use unsigned values. Then you're fine. Yeah, so the code just looks like this. If you're looking for the idea, how to code it, it's pretty easy. First 3 numbers minus 1. Okay. Next one, problem B. So yeah, okay, so this is kind of an interesting problem. You want to make all rows and all columns of a matrix palindromes. In one operation, you can increase or decrease a number by 1. What's the minimum number of operations you need in order for that to be the case? Well, the idea behind this is that if you have your matrix, I'll just draw a big box here because I won't explain it in too much detail here, but basically, if you have some space, if this space is a 1, or well, let's say this space is something, it doesn't matter what it is, we know since this column right here is a palindrome, this space corresponds to the same thing. Since it's symmetric around the middle, these two are equal. But also, we know this row is also a palindrome. So this thing here is the same thing as this one here. And then we also know this is a palindrome. So we know this top thing here is the same as this bottom thing here. Now, all 4 of these need to be the same. It doesn't matter what it is, it just matters they all need to be equal. In order to do that, whatever these things are, we'll have to modify them in order for them to be the same. So basically, you can imagine we've got some number line, and we've got 4 points on this number line in some positions. We want to move all of these points to the same point. We want to do that for the minimum cost. So we can, if we have like some point in the middle, then the total cost will be this value here, plus this value here, plus this value here, plus this distance here. It turns out we can move this over, as long as it stays between these 2 middle elements, we can move it over to either of them. So in code, I'm pretty sure I move it over to this right middle element if there's a tie, or just the median if there is an odd number of them. You can prove this is the best middle by thinking, what happens if you move this in one direction, and what happens if you move it in the other? So in this case, if we're like, let's say the thing we're considering picking is here. This is the number we're going to make them all equal to. If we move it 1 in this direction, then all 3 of these things have to pay 1 more. But one of them has to pay 1 less. If we move it 1 step to the left, then this one here has to pay 1 more. But these 3 here all have to pay 1 less. So it's plus 1 minus 3. So we want to keep moving it left. That keeps being true up until here. In this case, if we move it 1 left, then we have to pay 2 more, but we also get 2 more, have to take 1 fewer step. Right? These 2 need to take 1 more step. These 2 need to take 1 fewer step. So that's kind of a way of looking at it that proves that you can pick either median as the value you make these all equal to. I guess there's also some other cases you want to be careful of. So if you have 2 values like this, they're the middle of the palindromes, like row-wise. So it's only 2 values. And if you have an odd by odd matrix, you have the middle thing, which just occurs once. So you have to be careful how you handle that, I guess. For looking at the code, I make at first I read in the array, and then I make a Boolean array to say whether or not I have used each position. Then I go through every spot in the array, and I say, okay, like the 4 pairs of x and y's that are 4 positions that are relevant here will be x, y, x, the opposite y, the opposite x, and this y, and then the opposite x and the opposite y. So I go through each of those, and if I haven't used it before, then I add it to my list, and I say I've used it. And then I add the cost to bringing them all to the middle. So that's the idea for this problem. Make sure your cost is along, because it can get pretty big. And I think that's basically it. So just be careful with how you handle all of these extra side cases. All right, on to problem C. So for problem C, you want to know, yeah, this one I thought was pretty hard. I imagine there's a pretty sharp drop-off. unsolved for problem C. Not as sharp as I guess I would have imagined. I thought it would have been sharper. Maybe there's an easier way of doing it that I'm not seeing. But anyway, it was pretty math heavy, I think. So yeah, you have this string of digits, and you're gonna say, okay, you can remove any substring of digits, any continuous substring. If you remove all substrings and add up the total of the resulting numbers, what is the result under mod of 10 to the 9th plus 7? So that's the problem statement. How do you do it? Well, like a lot of problems where we're counting something, the idea is, let's say, yeah, so we've got like a bunch of digits here. Let's say this digit is a 7, and then we have a bunch of digits over here. What we're going to do is say, how much does this 7 contribute to the answer in total? That's what we're going to try and find out. Now, there are a couple cases. One case is we remove the 7. In all of those cases, which the range that we remove includes the 7, it doesn't contribute anything because it's not even there. So we're going to ignore those ranges. There are two other cases in which the range we delete is to the left or to the right. Now, if it's to the left, we know how much the 7 contributes because we know how many digits come after it. In this case, 3 digits come after it. So this contributes 7 times 10 to the 3rd under mod. So I won't write this mod part because it's implied everywhere. But it's 7 times 10 to the 3rd. That's how much it contributes. It contributes that much for each possible pair that's deleted on the left. Now, there are a bunch of ways we can delete from the left. In particular, we can delete this range here, this range here, this range here, this, or this. So basically, we have a left endpoint and a right endpoint. The left endpoint needs to be at least as far left as the right. So this is n choose 2, I guess, or maybe n plus 1 choose 2. Actually, what it turns out is this is n times n plus 1 divided by 2. That's how many ways there are here. In this case, n would be 3. So there are 3 plus 2 plus 1 ways of doing this. We can calculate the value for the left side pretty easily. Now the value for the right side is a bit more tricky. The reason for that is this 7, we don't know we don't know which digit the 7 is. It's hard to tell. So we have to be a little bit more careful for that. Basically what we can do is we can look at all of the ranges that could be deleted. So the first possible range would be we delete everything after this. In this case, what the 7 contributes is 7 times 10 to the 0. We also want to count the number of ways of doing this. There is one way of doing this. This is the only range you can pick that will get deleted, then it deletes everything to the right of the 7. Okay, that's the first way. Now, it's possible it doesn't delete everything, it deletes everything but 1. There are two ways of doing that. We could delete this range, or we could delete this range. So in this case, it's 7 times 10 to the 1 times the two ways of doing it. And then we can decrease the size of the range by 1. Now there are 3 ways of doing it. Now it's 7 times 10 to the 2 times the 3 ways of doing it. We can factor out this 7. We'll store the 7 separately. And now we want to store this 10 to the 0 times 1, 10 to the 1 times 2, 10 to the 2 times 3, etc. You'll notice when you move this over by 1, what happens is it'll be the same thing, but we'll add in 10 to the 4 times 4. This is backwards, isn't it? Or 10 to the 3. Yeah, 10 to the 3 times 4. We're going to move it over by 1. So again, we'll multiply it by, instead of multiplying it by 7, we'll multiply it by whatever this next digit is. So we'll take this value and multiply it by whatever this digit is. We can pre-compute all of these values for all like 10 to the 5th of them. We can like pre-comp all of these. Or we can store it as we go. Calculate it as we go. I store it as we go, but it might be easier to think about if you pre-comp them. So now for each digit, we can say, okay, if the range we delete is to the left, then we know how valuable the digit is. We can easily calculate how many times that'll happen. If the value is to the right, we can use this math to very quickly figure out what the total is. So yeah, that's the idea. Okay, code. it's easier to explain on paper than it is here. But basically, for the bigger numbers, it's n choose 2 times whatever the power of 10 is times this number. That's how many times this occurs, or the total value this contributes. Now for the smaller numbers, it's tricky. So it's this 10 values, right? It's the sum of all of these things. These are all added up. This is what I've maintained. So it's I times this value. In this case, it would have been like 7 times all of these values. Then I need to maintain a bunch of things. So first I need to maintain this power of 10. I call that 10 pow. So I keep track of that. I multiply by 10. The multiple increases by 1, so I increase the multiply by 1. The number of numbers that are bigger than me, that's for the n choose 2 stuff, I decrease that by 1. And then also this 10 values, which is the sum of all of these things, I need to add in the next factor that happens. So I add this in. Yeah, so that's the idea for problem C. I guess that works. On to problem D, returning home. So yeah, this one is interesting. I thought it was a good problem. The idea behind it, well, what's the statement first? So you have some grid, and you want to go from one position to another position, but the grid might be really big. So that's tricky. And the question is, what's the shortest path from them? So you can walk like along Manhattan distance, that's fine. But there are also these special teleportation panels, which is like maybe you've got this panel here and also this panel here maybe. So what you can do is if you walk down to here, then you can instantly teleport to one of these panels if it's on the same X or the same Y. Now we can walk a little bit this way and then teleport to this panel here. Then we can walk like this to the finish. So in total, we only have to walk like this A plus B plus C distance, which isn't really that far. Question is, obviously, what's the total time it takes you to get to the finish? Cool. So how do we do it? Well, the first observation you want to make is between two teleportation panels, when would you walk from one teleportation panel to the next? Let's say you're going to walk to the right from one to the other. It's only really beneficial to do that if from this one, if we have these teleportation panels sorted by X, we only want to walk right from one to the next one if these are like the adjacent teleportation panels that are like right next to each other and if they're sorted by X. If they're not, let's say you have this one here, you've got this one here, and this one here. You might say, well, maybe I want to walk like this. Sure, maybe that's fine, but you don't need to. Instead, you could walk right to this one. You could teleport up here. Then you could walk right to this one, teleport down here. These teleports are free, so you might as well just do that. So if we're going to build a complete graph of all of the edges that are relevant, we only need to include these edges here. In fact, we only need to include like a linear number of edges. We don't need to include n squared edges. Because for most pairs of teleportation panels, you'll never actually walk between them. Okay, yeah, that's the idea. So for basically like to summarize, what we're going to do is we've got all of these teleportation panels. We're going to sort them by X and sort them by Y. But I'll only talk about sorting by X. You just do the same thing by Y. When they're sorted by X, you add edges between these nodes in the graph. So these are weighted edges. And then we'll also add edges by Y. So I guess maybe I'll just draw those two. So these edges will be sorted by Y. So we'll add this edge here, sorted by Y. Maybe this edge here, sorted by Y. And this edge here, sorted by Y. So we've added all of these edges. This is order like 2n bidirectional edges. So these are for all of the teleportation panels. We also have the start and the end. So you've got the start one. We'll add an edge from the start to everything. That's pretty easy. We'll also add an edge from everything to the end. That's also pretty easy. And the start to everything, those are simpler because these you either walk through the X or the Y. To the end, you have to walk the entire way because you can't teleport to the finish. So this is like just the Manhattan distance rather than the min of the dx and dy. Yeah, okay, that's it. So then once we have all of these edges, we just run Dijkstra's algorithm on it, and that'll give us our answer. Then to calculate the final answer, we need to consider it's possible to walk from the start to the finish. It's also possible to walk from the start to some node, then walk from this node to the finish. And I think that might be easier. To handle this, what I did is, I guess there are better ways of doing this, but like you could probably do this all in one Dijkstra's. But I did another Dijkstra's from this finish to handle all of these edges. I just thought it would be easier. It wasn't too difficult, I guess. So yeah, here's the idea. So I have all of these points. I store them as vectors. So a vector just has an x and a y, and then has, this is like the node part of it. So it's got all of the adjacent things and the cost of all of the adjacent things, like the cost of the edge to them. And then this is like the distance from the start point. This is the distance from the end point. Okay, anyway. So first I sort all of the points by x coordinate, and now I add edges between adjacent ones. The cost of each of these edges is the difference in x between them. Then I sort by y. I add edges between all of the things that are adjacent by y. The cost of the edge is the distance of the y between them. And then for all of the points, I add edges from the start to them and from the end to them. Then I do my two Dijkstra's algorithms, or Dijkstra runs, I guess. One from the start, one from the end. And now I store d2 as the distance from the end to something, d1 is the distance from the start to that thing. You can either walk straight from the start to the end, or you can walk from the start to something and then walk from the end to that thing, but backwards. And I just keep track of the minimum of all possible answers. So yeah, that's the idea for problem D. Okay, problem E was the last one that I ended up solving. So I didn't solve the next one. It's getting some hacks, so there's a non-zero chance that my solution is actually broken and will fail system tests. And if it is, take everything I say with a grain of salt. But I think I have the right idea. It's just you have to be kind of careful. So the problem statement is you have some string. You want to say for each suffix, what is the lexicographically minimal string you can create, where you can do certain operations in order to like create a new string. Those operations are anytime you have a continuous range of, like you're going to pick a bunch of pairs of elements where the two elements are next to each other and are the same element. In this case, you could pick like both of these Ds. Then you can delete the pair of Ds. And then afterwards, you'll be left with just ABC. So you can do this as many times as you want. And for each suffix, you want to try doing this. The question is, what is the lexicographically minimal answer you can get for each suffix? Now, since the total output might be like very big, it might be n squared, then you, it's not actually n squared. It's only 26 long. Why was it not just 26 long always? Oh, because you could have Z through A, then Z through A. You couldn't delete anything. Yeah. So you might not be able to make any operations at all. Yeah, that makes sense. So it can be very long. The total output could be n squared, so you need to do this ... thing instead if it gets really long. All right, so the idea behind it is we're going to use some stack of answers, and we'll like keep track of this in a smart way. So we can like make all of our decisions greedily, and we're going to do them building the answer up from the end to the beginning, then we'll just print all of our answers out in reverse order. So let's say the string, I think I talked about BAACC AAB. This is maybe smart. Okay, maybe BB. There you go. Or, yeah, sure, this is fine. Okay, so first we'll look at this B. We don't have a choice, we have to keep the B, and that's it. Now we have this other B, and we see these two are the same, and this like empty string is lexicographically smaller than anything, so we'll delete both of them. So now we just have the empty string. Okay, now we see this A, And I guess let's add a third B here. That makes it more interesting. That way we'll hit all of the cases. So we see both of these B's. Okay, let's start again. First you got a B. You can't do anything, you have to keep it. Now you have another B. We're going to delete both of these because the empty string is lexicographically smaller. So we have just the empty string. All right, now we have this next B. We have to keep the B, and that's it. Now we have an A as the next character we're going to add. For this A, we actually want to keep the A because it's lexicographically smaller than the B. So it's beneficial to have the A. This other A we also want to have because it's also like beneficial to have because it's smaller than this B here. So we choose to keep it. Now when we have this C is lexicographically bigger than the A, so we would like to delete the C, but we can't because we have like the wrong number of them. And now instead of comparing things to the B, we're comparing them to this A here. So now we see this other C. We have an even number of these C's, so we can delete all of them. And we'll pop them off the stack and then consider this A as the next thing. So we remove these from the stack. Now we have these two A's here. And we know the reason that we kept these A's, I guess, was because we had this B, this previous B, which was beneficial. Ooh, am I gonna get roasted by this? What if we have ACCA? I've got 2 minutes left. Let's hack myself. Okay, good. I think that's the break case for everyone. Yeah. Yeah, so you have to be careful not to delete those two. But that's the, yeah. So when we see this A, let me just be very careful here. Yeah, okay. So if we're the same as, ooh. Okay, I am actually safe here, but just barely. Yeah, it works in a confusing way, but it is right. So I don't think I'll be hacked. I should be fine. But the important idea is that you have to be, I guess, careful not to delete A's across the border, if that's possible. If you have something like A, B, B, A, because you aren't allowed to delete these two A's, even though you'll pop both of these B's off the stack. So okay, that was a bit of a messy explanation. I'll walk through the code and I think that'll be good. So here's the idea. We have the line of input and then the answer. Also have a stack, which I'm just doing kind of manually, and then I store the index of the front of the stack. So if I want to remove from the stack, then I just decrement this variable. Yeah. So if the stack is empty, then we need to take this next character. We don't have a choice. So we do that here. If the stack isn't empty, then we check if this is the same character as the previous character. Now we want to delete this character only if only if this character, if this pair of characters if deleting them will improve our answer. So that happens if the next important thing on the stack, the next thing that's different, is smaller than us. Then we want to delete us so those things come to the front. Otherwise, if that thing is bigger than us, we want to leave ourselves. That way we push that farther back. We just have as many A's as possible in the beginning, basically, before we have any B's. So yeah, so that's the idea here. if either or if those things are both the case, then we remove from the front. Otherwise, we add this thing to the, it's really the stack. Otherwise, what happens, this means, so this is the last case, which is we're different from the front thing. In this case, the new like last element will be whatever element was at the beginning of the stack, and then we need to push ourselves onto the stack because it's basically we're a new type of element. Now this thing will never get removed because it will always fail this check. So this thing is now like permanently on the stack. Then we build the answer format. I'm not going to cover this. This is just like you have to be careful, and then you print the answer at the end in reverse order. Okay, awesome. Yeah, so that's the contest. I enjoyed it. I didn't spend maybe as much time on F as I could have, but it was pretty tough. I'd like to see how you do it because I don't know. Looks like about 17 people got it. Yeah, I don't really have any good approaches to it. Wait, TFG, is this, he's the Brazilian guy, right? Yeah, I think he's friends with JCB or whatever. I don't know. I wonder, he may have been a guy who answered my question a long time ago. I'm not sure. So anyway, yeah, fun set. Thank you for the problems, whoever wrote it, to the authors and the testers. I appreciate it. And yeah, hopefully the editorial was helpful, or I guess the video editorial here that I just made. But the editorial might explain F, in which case you should read that. So, all right, thanks for watching. Hope you have a great day, and hope your rating went up if this was rated for you. Goodbye.